No, no, on one end, I'm going to hook up my laptop for you guys. And on the other end, for the Zoom people, I'll have my iPad hooked up. And then everyone will be happy. No one will have epilepsy. Because yes, the thing is flashing. Wait, actually, it's not flashing. Hey everyone on Zoom. Sorry, we're having a little bit of technical difficulties. We'll start in like 3 minutes. Hello. Please sign on the record sign the whatever.
Wow. You starting it? Yeah. But the thing
Can
is,
anyone
my
can
lab
everyone
teacher,
hear me on
no,
Zoom?
he
Hello?
so we all finished the lab and we were gonna do a lab report for it. So just do a lab report on whatever you did.
Can anyone hear me?
Did he give you a range of speed? Because it was so lab was so broken because we didn't do the lab individually. We couldn't get them parts. So like we had groups instead of like two people to complete an experiment. We kind of did groups. Yeah. So it's like whatever experiment, like I did not carbs, I did proteins. So it's like just write a lab report on protein. Just proteins? Just proteins. Oh, you great. Oh, because we were in groups, so we were like cycling. No, we didn't cycle. Too. I guess maybe you produced much. I mean, he's the only one reading.
Okay, good. I'm glad that you guys can hear me.
So he passes me. I don't care. My guy told me I'm need
Yeah, under me.
stuff. He gave me no left to right about.
The touchpad, right?
That's yeah. That little flow.
Yeah.
Papers in the future, you can try and basically
It's a,
different
it's a check.
if you really want to make it good. But
Yeah.
I got one Kingman.
Front other side.
Not sure. I'll make the same mistake again. Oh, yeah, we got rid of these. From the moment that he's ready.
Oh, okay.
Here, of course, my I changed. No, I can't laugh.
This one goes.
Two question. Two question.
Yeah, it's plugged in.
It's like a scientific method.
Okay, right? Yeah.
One number multiplied by another plus another number. It was yeah. Press
Oh, is it working? No, this is from my laptop with the HDMI. Support me?
yeah. I was bunch of test tubes like oh okay. It's all sugar. I'm just gonna show you some of the reactions, and you're just gonna. Oh really? You did. You know.
Yeah.
The first question is like there were actually 9, 4, 6, 3, 2, 1.
So
Then he said it again. It's number 5 again. Like I guess
yes.
they don't really
Might be a bunch of like cables that
what is mine? My fire last. He was like, oh, you know, last week. So it's like, oh, our first lab, we office first because I don't feel like you guys buy the lab manual. I'm just gonna you have it online here. Just use that. He's like, my office is my backpack, so I don't really like caring about people. Make sure you buy the most as soon as possible. Make sure you get all your lab coats as soon as possible. That one I guess makes sense, but yeah, he's a funny kid.
Okay. Hi guys. Gonna get started.
My lab just started. I saw Haji guys after that.
Yes.
And I was like, it's fucking with like the I swear.
Hello everyone. Hope you're all doing well. My name is Luke. Sorry we're having a little bit of technical difficulties with projecting the iPad, but that's okay. Yeah, we're gonna get started. We're gonna be focusing a lot on section 2.3, which is all the quantum number stuff. And I hope to clarify things about that quantum numbers because I know quantum numbers is a very abstract concept. Who here like I guess like a show of hands, I guess like still a little confused about like Thursday's lecture. Anyone who's a little iffy about it? Yes, I'm gonna go over it. That's my job. I'm actually going to I'm gonna kind of reteach it a little bit because I don't really like the way Professor Yusuf teaches this one section. No shade on him. It's just kind of that's basically how the textbook teaches it. They teach it through what's it called? Through S like first talking about the s orbital, the b orbital, the b orbital, whatever orbital, right? The reality is that you don't really need to have that foundational understanding to know what they are. I'm sure is everybody here I guess like what's the word? Like, is that yeah, acquainted or familiar with like wave mechanical model? Does anyone know what that is by chance? It's the stuff that you guys are gonna learn next lecture, but basically like stuff like 1s2, 2s2, 2p6,
Yeah.
right? If not, that's okay as well. I want everybody to open up like a periodic table if you guys have it. Yes, I'm going to do that over here.
I just
I'll be right back. Yeah, no problem.
keep the laptop. Yeah.
Okay.
I swear.
Yeah. Go over it. Yes, I will go over quantum numbers. So let's get moving. So, before we do the periodic table, we're just gonna like hash out some of this stuff. You guys are gonna need to know like you guys are gonna need to know Erwin Schwarz, blah, 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 whatever, right? What he did. You're gonna need to know Heisenberg, what he did. De Broglie, you're gonna need to know what he did with whatever quantum mechanics, because I keep emphasizing this every SI session. All the scientists will be tested. All the scientists and their findings and whatever the heck they did will be tested. There are probably gonna be like maybe like 4 or 5 questions on it. So pretty important thing considering the test was gonna be around 30 to 35 questions. So let's keep moving. So we got the dual nature.
We don't have that much on.
Just their findings, right? De Broglie, right? What did he find? He found that all matter exhibits electromagnetic radiation, so they exhibit wave and particle-like things. You might need to know his equation, not to do any sort of thing with it, but to understand, like, I guess what is, like, what it's trying to express here. So, like, it's showing that matter and any kind of matter has a wave kind of particle to it.
So do we get know exactly what the other three of the slides before this.
Yeah, I mean, they're probably, we're gonna.
He didn't really say.
Yeah, Schroeder, like, he's gonna talk more about it next lecture, but for now it's okay. Yeah, yeah, that's totally fine too. So yeah, no problem. Okay, so this is a very basic question that I do not. Oh, I do. I need it. Okay, so yeah, what on Zoom as well? You guys could type in the chat. But yeah, who discovered this? Who discovered that all matter exhibits wave and particle-like properties? B, yeah. All right. What did Rutherford do?
Coil.
Nice. What did Planck do? Planck's constant. He quantified energy. He realized that energy can be photons, right? He realized that energy can be expressed through photons, which is what Planck's constant is. It's a packet of energy. All right. Schrodinger we did not talk about yet, so I'm not going to test you guys on that. All right. Okay. I hope everyone on Zoom is okay. All right. So the answer is B. Okay. Okay. Moving on. So, yeah, like you might need to know a little bit of this experiment, Davison-Germer experiment, just kind of like understanding what's happening here. Like the electrons are essentially getting diffracted, and diffraction is a property of waves. Waves get diffracted, like light waves, they get diffracted off of water or some reflective surface. Same thing with electrons. Electrons are getting diffracted. So knowing what this experiment serves to do, it's proving de Broglie's hypothesis, which is what I wrote here. Like, whoa, crazy. Okay. All right. So yes, this is
Can you go back up? I didn't finish writing what you wrote.
no problem.
Hey,
No problem. Oh, okay. Anyways, yeah. So this is basically showing that electrons have wave-like particles, and then this is another experiment that shows this. If you were to, Yusuf already went over this. Basically, like it's exhibiting a wave-like particle by the way that it is spreading out through that slit in the wall. So yeah. All right, so this is the thing about Schrodinger that you're gonna need to know. It's that why did that? Don't know what. Okay, all right, that's interesting. Okay, so basically Schrodinger, right? He found that he postulated a equation that shows like the probability of where an electron will be. Basically, there's going to be more on Schrodinger later, but for now, that's all you really need to know. And he's described it with wave mechanical functions or whatever, wave function. And that's where the orbitals come in. Okay? This is all very, like, just, you kind of have to know it to know it. Stuff about Schrodinger and stuff about Planck, the stuff about de Broglie, whatever, right? All right. Are you guys with me? Okay. We're gonna lock in right now. Okay. This is gonna be a very informative thing today. So okay. So all right. Okay. Which scientist before I go over, yeah. Okay. All right. Which scientist is credited to creating an equation that governs the wave function of the quantum model? We just went over this. Yeah, what do you guys think it is? B, yeah, Erwin Schwarz, whatever his name is. What did J.J. Thomson do? You guys remember this? Club pudding model. What else did he do? He did an experiment.
Charged math.
Yeah, charge to mass what? Yeah, charge to mass. Yeah, good. Yeah, charge to mass ratio. He did cathode rays. He found the charge to mass ratio of electrons. Perfect. And then yes, club pudding model, whatever. What did Hantaro Nagaoka do? What did he do? He predicted what Rutherford would later prove. Yeah, He might need to know that.
It's
Yeah, we very briefly went over him. I know it sucks, but yeah.
not even on the. Wait, he said his name
not
for
on
like
the
0.2
slide.
seconds. What did he do?
Yeah, he just basically you know like what Rutherford did? Like he did the Goldfield experiment, showed that there's a positive nucleus and then the thing is around electrons are around the nucleus. He like basically like predicted that model. So like J.J. Thomson did the plum pudding model, he did the actual model. That would later be proven by Rutherford.
So
Alright.
that one was proven by Rutherford and J.D. Thompson was disproven.
Yes. Very good, very good. Yes. What did Albert Einstein do?
MC squared.
He did the photoelectric effect. He saw that with higher energies of light, electrons can escape and be flown off. If when he did blue light is a higher frequency, right? Lower wavelength, right? And then yeah, the electron got taken off. Yeah.
Are we gonna have to know about the Bohr model?
No, not really. Just need to know what Bohr did. Bohr founded principal energy levels in electrons, and that's what I'm actually going to talk about soon. So yeah, how is everyone on Zoom? Can you guys text me if you guys are okay? I hope you guys are okay. I really hope you guys can hear me. Oh, we're good. Okay, that's great. All right, moving on to electrons and atoms. This is where everyone is a little scared and stuff. So, all right, quantum numbers got nothing on us. All right, guys. It's all just numbers, okay, at the end of the day. You know, we've done this, not that we've done this, but it's okay. It's okay. We got this, okay? So I'm going to point you guys all to the periodic table, okay? So the periodic table, can anyone tell me what I guess like yeah, the questions on the board, what does each row represent? What does each number represent at the top? Yeah. No, I'm trying to give you guys are gonna learn this next lecture, but I'm just asking. Yeah.
I think each row is the energy level.
Yeah, energy levels. Yeah, that's good. All right. What about
Oh,
Yeah.
number on the top is a different group.
okay, yeah. No, I meant to say what is these numbers up here?
Oh,
Okay, what does this represent?
number of protons.
Okay, good. All right. In a neutral atom, right? Number of protons equal the number of electrons, right? You need a neutral charge, right? 10, -10, right? Plus +10 equals 0, right? Neutral is 0. All right. So another good question. Does anyone know why the periodic table is shaped like this? Well, we're gonna get into it, but a little preview, right? Is that this is the S block, this is the P block, and this is the D block. All right. We'll get into that later, but and then this is the F block. But that's for later, okay? Okay. So I'm gonna go into a little bit of Bohr stuff. You don't really need to know this stuff, but essentially, yeah. Electrons have principal energy levels, right? Like hydrogen, for example, right? +1 in the middle, right? Number of protons is 1 proton. It has 1 electron, right? Okay. Helium would have 2 with 2 electrons, right? Right. All right. Everyone following? But then when we get to what's it called? Lithium has 3 protons, right? It has 1 electron, 2 electrons, but then oh wait, now we have to fill up the second energy level, right? So now we have to add another electron, right? Okay. I hope you guys can see where I'm going with this. All right. But yeah, so basically with the writing electron configuration, right? Is everyone familiar? How many of you guys like took chemistry in high school? Went to chemistry in high school, right? So how many of you guys are familiar with like the notation of like 2 dash like 8 dash 18? Are you guys familiar with that? All right. So these are electrons, right? So what this represents, right, is if I were to count the number of electrons in helium, right, there would be 2 electrons in the first principal energy level, right? If I were to count the number of electrons in neon, though, there would be 2 electrons in the first principal energy level, and then another 8 right, making 10 electrons, okay? And then vice versa with argon. Argon, or not argon. That's not right. With
You can still do it with argon. We can do the 18 because then it doesn't go to.
288, sorry guys. But with argon, right, it would be 2 electrons at the top, right? And then another 8, and then another 8, right? So that's like basic electron stuff, right? Now, do you guys remember the wave mechanical model at all? Like basically with the wave mechanical model, right? With the SPDF, right? Basically, the way to represent this, just in general, is you would have one S2, right? And then that represents the first principal energy level, right? First principal energy level only has the S block. But then with the second principal energy level, now you have 2s2, right? And then you have 2p6, okay? Right? And that represents neon, right? And then you go on to the next one, 3s2, 3p6, all right? Does everyone see where I'm going with this? Or at least understand a little bit of what I'm doing? You guys will go over this in lecture. All right? All right? So, does anyone know what box orbitals are? Like orbitals, oh, I should be writing this on the thing. Yeah, Ruse. Okay. Does anyone know what box like box orbitals are? I guess. I don't know if that's the right word to describe them. Like, I guess representing electrons in boxes. So like, for example, like this. Does anyone remember this at all? Okay, that's okay. So basically, one way electrons can be represented in an atom, right, is with this box notation. Okay, so 1s2, right? Next principal energy level, what would it be? It would be, can anyone guess it? 2s2, right? And then what would it be the second one? 2p6. How many boxes would that get?
2 extra boxes.
Yes, making 3 boxes, right? Okay.
Oh.
Yeah.
Okay.
Yeah. I get it, I get it.
2p6, right?
Yes,
Next,
yes.
next one. Can anyone tell me the next one?
3s2.
And then next one. 3p6. All right. So how many boxes would that get? Okay. So basically, what quantum numbers does, okay? All quantum numbers is doing is, how can I identify this electron? How can I identify this electron? All right, or how can I identify that electron? And we're going to get into that momentarily. All right, but is everyone following with me so far? All right, with the just like you guys are going to learn this on Tuesday, but I'm just trying to illustrate how we can represent electrons. And now the point of quantum numbers is to actually figure out where those electrons are. All right, everyone got good so far? All right. It's okay. It's okay. You guys will be okay. Okay. So, I should write this box. Good. Okay. Moving on. Okay. I already asked that question, but I hope you guys know what basically with the wave mechanical model, with this, right? The way it just expresses like the number of electrons in the thing, right? In an atom. So, for example, with helium it would be 1s2, right? With beryllium it would be 1s2, 2s2. Okay? And then with neon it would be 1s2, 2p6. Okay?
I forget like carbon, it'd be like 1s2, 2s2, 2p2.
Yeah,
Okay.
it would be cut. Yeah, it would be like that. Alright. So how many electrons does oxygen have? Alright. Can anyone tell me? Yeah, 8. Alright. Does anyone know the wave mechanical model of oxygen?
2s2.
Yeah. Oxygen's wave mechanical model. 1s2, 2s2, 2p4. Alright? Alright? And how would you represent the box stuff?
Like that.
Yeah, how would you represent that?
So you do.
One
So you
singular
have to do
box.
the first line, the second line. But for the 3 boxes that you have, you have to take out two electrons in one that are going in one direction. I don't know if that made any sense.
I get what you're saying. So, what Devinder said, right, is you want to have one box, right? This represents the 1s orbital, all right? And then you have another box which represents the 2s orbital, and then you have a third box, right?
We don't fill up all of them.
We fill up the one,
only
two,
fill up-
and then
One, two.
So
One,
why
two.
is one S one box and two S also one box?
Because we have multiple s orbitals in a thing.
Yeah, I know, but so then what's the point of putting 1, 2, 3, 4, 5 if it's the same box?
Because this is a different principle. This is another energy level. So this is the first energy level, right? And then now that we're in the second row, right? Now there's a second
So
energy
is
level.
that thing next to it the 2P?
Yes, this is 2p. This is 2p, this is 2s.
Okay.
All right. Sorry for not labeling,
Cool.
but
No,
yeah,
I
1, 1, 1, 1. You guys don't need to realize why I did that, but
only 4. Your team.
yeah, it's because of Hanzul, but we haven't gotten over Hanzul. Why I know this is very much breaking your brain a little bit because, yeah, for one, you guys haven't learned this stuff yet. But the whole point of this is to kind of illustrate how quantum numbers identifies these electrons, all right? So, let's move on. You guys seeing the stuff I'm writing. Okay. How many electrons? Okay. All right, so I'm not gonna really dwell in on this that much because yeah, the wave mechanical model is what you guys will learn later. But essentially, essentially, yeah, basically every electron is existent in some sort of orbital, whether it's the s orbital, whether it's the p orbital, the d orbital, or the f orbital. All right, whether you are a fluorine atom or a hydrogen atom or an iron atom or whatever atom, there's electrons in these orbitals that are constantly moving, right? And that's what Professor Yusuf was trying to illustrate with the icon.
yeah, you closed it around me. I was
Sorry.
really right there.
My bad. That's what Professor Yusuf was illustrating with the circles, right? So this is an s orbital, right? And then remember he illustrated the 2s orbital, which is like a bigger one with like a little thing in there, right? And then 3s orbital is a bigger one, right? What I'm trying to illustrate to you all is that if you guys look at the periodic table, it's built like that, right? Obviously, the first row is hydrogen and helium, right? That would be 1s2. Then this one would be 2s2. This would be 3s2. This would be 4s2. All right? 5s2, 6s2, 7s2. All right? And that's kind of what I'm trying to illustrate. The beauty of the periodic table is that it is the beauty of the periodic table is that it is arranged in that way to represent the wave mechanical model, to represent the waves, to represent the different orbitals, the s orbital, the p orbital, the d orbital, the f orbital, and that's about all the orbitals. Okay. I'm not going to that. Okay. So if I were to, I guess, say, what is, how would you represent the first electron in hydrogen, right? Hydrogen's electron, right? There's only one electron, right? And it's in the first principal energy level, right? So how would you represent that one electron? All right, 1s. Okay. So by our naming whatever, right? N would equal which one? You guys know?
Let me 0.
N would equal 1. First principal energy level. N equals the energy levels. Okay.
L would be 0.
L is 0. Yes. L
L is 0.
equals 0. All right. 0 equals S, the S orbital. All right. What L equals is the type of orbital then, whether it's S, P, D, or F. Okay? With ML, right, that represents what type of orbital, it's like what specific orbital it's in. And that will be kind of later illustrated. all right? And then ms represents the spin on the electron, right? So this is a downward, it doesn't really matter, you can do plus or minus, but because it's only one electron, you have to choose one of those. All right? Is everyone following with this? Okay? It doesn't matter what spin, but if there's asking one, what's the one electron, you have to do one spin. Like, you can't do plus or minus. You have to do, what's that?
Just like pick
You pick one.
positive or
You
negative.
just pick one, yeah. All right. All right, let's move on to nitrogen, right? Nitrogen. How many electrons does nitrogen have? Can anyone tell me that? What's that? 7 electrons, right? Okay, so 7 electrons. This is hydrogen. All right, let's go nitrogen. Nitrogen. Okay. Nitrogen is illustrated by 1s2, 2s2, all right, and then 2p3. All right. Okay. Don't worry about this right now. Don't worry about how I figured that out. This just represents the electrons, okay? There is 2 electrons in the first principal energy level, and then there's 5 electrons in the second principal energy level. All right? Everyone following with me? Okay. All right. How would you represent, I guess, a electron in the p orbital of nitrogen? All right. How would you represent p orbital electrons in p orbital? Okay. So what's the stepping? What you guys had active on this? So what would be the first step to do this? Or sorry, 2p orbital. All right. What would be the first step for this? Identify what the energy level is, right? So what would n be? Yeah, n will be 2. All right. Now what would L be?
Can you explain again why it is equal to 2?
Yeah. So basically, what I'm asking for this question is for nitrogen, right?
Yeah.
Right. How would you represent the electrons in the 2p orbital? All right.
Like 1, 2 is taken. That's like the first one. Like the second one, that means that n equals 2.
What's that?
Well, because like it has like the first 2 electrons in like the first little like orbital, and then like the fact that you're in the second orbital, that means n equals 2.
Yeah. So
Oh, okay.
what n equals, right? It equals the principal energy level that electron's in.
Yeah.
Okay. So because I'm asking for 2p, right? It's in the second energy level. Okay. What would L equal? 1. Right.
I have a question.
Yes.
If it was an electron, was it 4? Third.
4d. 4d n would equal 4 because it's the fourth principal energy.
So it's like the coefficient. That's
Yes, it is the coefficient. All right. Now, what is ml? Yes, -1, 0, 1. Coincidence that there's 3 of these? There's 3 orbitals in the p. All right. What I'm trying to illustrate to you is that wave mechanical model that you may have learned in high school is synonymous with quantum numbers. All right. Anyways, so now the ms, right? Ms is the spin of the electron, right? So how would you represent? I guess I can't really do that right now, but nitrogen's electrons would be this, right? You guys will learn that tomorrow. But yes, how would you represent these 3 electrons? They're all the same spin. So how would you represent it? What's
It
that?
has to be not, it doesn't matter if it's like.
Yeah, it does. So basically, with like, you guys will learn it on Tuesday, but essentially, when you fill up an electron, like these things, right? It has to be the same spin originally, and then once you're done with it, then you fill up these with a different spin. So it would be plus 1/2, right? And then you do ms plus 1/2. I will erase this so that you guys can see that. MS. All right, so that would be how you would identify the electrons in the p orbital. All right, is everyone following this? All right, now I'm gonna throw a little question here. How would you represent the atoms? How would you represent the electrons in the 2s orbital? So 2s orbital. How would you represent this?
Equals 2. So Lx equals 0.
All right. What does LF represent?
S orbital.
Yes. I mean,
The orbital is-
the type of orbital,
Yeah.
right? What does what would ML be?
0.
0, right? Because you can't have any negative integers with that, right? And that's a synonymous with the fact that there's only one orbital in the s orbit, right? So that would be ML. All right, and then what would MS MS be?
It's minus 1/2.
Yeah, plus or minus 1/2. Perfect.
Why is L zero?
Because yeah, ML, what it represents is the orbital. So L represents the type of orbital. L represents the number of orbitals in that orbit, right? So L, what this 0 represents is that this 0 represents the s orbit.
Get zero.
The 0 came from the fact that it is, this is a s orbital, right? So any sort of if I were to represent all the electrons in the s, like the second energy level, right? It would be n equals 2 or n equals 1, but that's beside the point. Okay, and then L for 2, right, could represent 1 or 0, and for 1 it could only represent 0 or 0. Yeah. So basically, the reason why I chose 0 though is because 0, right, the number of integers is only one integer, right? Which is how many orbitals can be in the s orbit. All right. So yeah, there's only one number from this, right, which represents the s orbital that you guys will learn on Tuesday. Okay? But yeah, that's how you would represent the 2s orbital. How would you represent the 1s orbital from nitrogen? Would anyone like to give this one a shot? Yeah.
N equals 1.
So 1s, right? So n equals 1, right? What would L equal? 0.
ML is 0.
ML is 0, and then what would MS be? Plus or minus 1/2. Good. All right.
So would you have to write out like the set of quantum numbers for each electron individually?
It really depends.
Because like I know the other day when
Yeah. Yeah. What were you saying?
no, I know because the other day we did a sample problem and we had to write out all 6.
Yeah, no, yeah, you're gonna have to do it like the way that you guys did it in class.
Okay.
All right. But yeah, I hope you guys can see the points being illustrated. Yeah, I hope that this is okay. Because yeah, what I'm trying to illustrate to here, right, is that quantum numbers are essentially just identifying the electrons and where they are in the atom, right? And just like through the different orbitals, right? Orbitals are essentially where the electrons don't reside, right? You can specify specifically what atom you're talking and what electron you're talking about. All right, we're gonna do one more problem with this. All right, so I hope you guys are ready for this. Okay, all right, let's try chlorine. All right, can anyone tell me the number of electrons in chlorine? 17 electrons. Perfect. Good. All right. What would be the number of electrons in the first principal energy level? 2. Yes. All right. The way that Devinder may have counted it or may not have counted it is you just count the top 1 and then you count 2. I can't. I'm getting old. Yikes.
Old.
Okay, so Yes, 1, 2, right? How many is in the next one? 8, right? Because you guys can count 8, right? Now, what's about the next one? Yes, 7, because how many are here? 1, 2, 3, 4, 5, 6, 7. Perfect. Okay? Now, what is this energy level? What? Yeah, this energy level is 1, all right? This is the first energy level. What's this energy level? 2. Second one. What's this energy level? Okay. Do you guys know what valence electron? No, you guys haven't learned that yet.
It's like the ending one, right?
What's that?
It's like the last electron. Or
Yeah, it's like the
It's like
outermost
the
electron.
last.
Yeah.
Yeah, but I'm not gonna go into that
Yeah.
right now. Okay. Now, right? How would you represent this? Well, how would you represent the first energy level electrons? Would anyone like to give it a shot? Okay. Anyone else would like to try? Yeah. Yes, 1s2, but how would you represent that with quantum numbers? Yes, n equals 1, okay? L equals 0, right? Because what does L equal? Yes, well, L equals the type of orbital, 0 equals the s orbital. All right, what does ML represent? Yeah. ML represents specific orbital. And then what would MS be? What's that?
Spin.
Yeah, the spin. So it'd be plus or minus 1/2. Okay, so this represents this first energy level. All right. Now let's try to represent. Let's try to represent the s orbital in this. All right. So can anyone tell me what the s orbital is for? SP? Can anyone tell me what the s orbital is for?
That says SPD, right?
Yeah, this says SP.
N equals 2.
Yes. So n equals 2. Okay. L equals 0.
0.
ML equals 0, and then MS would be what?
Plus minus 1/2.
Plus or minus 1/2. All right. How many electrons am I representing here? 2 electrons, right? So 2 electrons, right? This is only in the s orbitals, right? So how would I represent this right now? It would be 1s2, 2s2. Okay? Is everyone following with this? All right. Are you guys good? Okay. Now let's try to represent
P1.
P1.
So still the second.
Yes, it's still in the second one. So what would the P1 be? What would the quantum numbers be? You guys want to give it a try?
I'm so good.
What's the questions? So 1 and 2, right? This represents the first principal energy level, right? This little amount of electrons, right?
You were working 2-8-7
So
from that.
So basically, right, when you have a neutral atom, right, you have the same number of electrons as you do protons, right? So basically, okay, there are 17. Oh, what is that? There are 17 protons in chlorine, right? That's the atomic mass. Atomic mass equals proton number, right? So how many electrons would there be in chlorine? You know? Yes, 17, because the number of protons equal the number of electrons in a neutral atom, right? So now, what we did, right, is we counted the number of electrons. And the way that I did it was I used the periodic table. So you start with the first row, right? The first row, there's how many elements are in the first row? 2 elements, right? And they also represent, you can also represent them as electrons. What about the second orbit? The second one,
Okay.
8, right? And the next one's 7. So what this is representing is that this is the second one, this is the third one. All right? And now, if you look at this as well, you can see this represents S orbital. All right? You see how in the 2s one, right? This one is an s orbital. This is 0 equals S. All right? These electrons that are represented here in this 2-1 represent the electrons in the chlorine atom of these two, like in this S block. All right? Is everyone following? Everyone getting? You guys get it? Okay. How you doing, Spiro? Okay. All right. What I'm trying to demonstrate is that I don't know what I'm trying to. I'm trying to demonstrate that there is a pattern between what you may have learned in high school chemistry versus right now. Okay. Are you guys sticking with me? Are you good? Yeah? Okay. What about the p orbital in the second one? So 2sp.
I think I got it. Can I try?
Yeah, go ahead.
So like I have for the P for the second I have N equals 2
N equals 2. Good.
and then L equals 1.
L equals 1. Do you guys know how you got L equals 1? All right.
Right, because P means L equals
Yes,
1.
yes, very good. All right,
And
what
then,
does,
ML equals -1, 0 and 1.
okay?
And then I'm still confused about the MS. Is it I don't know how
It's always plus.
It's just plus or minus.
yeah, that's what I have, but like how would you know if it would be plus or minus?
Well, normally, so it depends on like the electron. You'll figure it out next lecture.
Okay, yeah.
Because this
Save
I
it
keep
for-
went over more because it's kind of hard to explain all of electrons if he only goes over half of it. Okay,
Yeah, let's wait till tomorrow and just keep going. I think
Yeah.
that's fair.
but basically each of these orbitals, right? How many electrons can be in one orbital?
2.
Anyone know? Yes, 2. So how many electrons in total are in these
2 or 6.
2, 4, 6, right? Every orbital, here, this is a good rule of thumb. Every specific orbital has 2 electrons, all right? And that's represented by the MS, all right? So this has plus or minus 1/2. This also has plus or minus 1/2 electrons. This also has plus or minus 1/2 electrons. All right? Are you guys following? You guys got it?
Question.
Yes.
So you wrote for 287, you wrote SPD. Wouldn't it just be SP though?
Yes, it would be SP. But remember also, if I were to, in the third principal energy level, there is the 3D block. There is a 3D orbital. There's a d orbital in the third one. So that's why I wrote SPD, because you can technically represent that in the third orbital. But yeah, what else got questions? All right.
Can we do it though for like the third one? Like all 3 of them? Or like just SP?
Yeah, you
Alright.
could do that as well.
Yeah, please.
Okay. We'll do that soon. Okay. Now, let's go to the third principal energy level. So all of this is being represented right here. Okay? There is 6 electrons in this. All right? Are you guys following? Right? There's 8 electrons in total being represented. There's 6 electrons here being represented. All right? Everyone following with this? Okay? Now, the third principal energy level. Feel bad. I'm like neglecting everyone on Zoom because I don't know how to explain this without okay, whatever. Okay. So this one represents now these 7 electrons, okay? All right. These 7 electrons, the third principal energy level. What does N equal for the third principal energy level? 3, right? N equals 3. All right. Now, let's try to represent only the S one. So what would the SL be? 0. Ayo. That's good. That's good. That's very good. So now what would ML be? 0 as well, right? ML is 0. And that's because there's only how many orbitals in the S orbital? 1. There's only 1 orbital in the S orbital, which means how many electrons can be there? 2 electrons. There you go. You guys are good. You guys are getting better. All right. Plus or minus 1/2, right? So there's 2 electrons being represented here. Okay? Now let's go to the 3p one. All right? Okay. So 3p1, this is S. I'm sorry, I'm really bad at displaying like visually, okay, but it's okay. So what would N equal for this one? 3, yes. N equals 3. What would L equal for this one? 1. All right, L equals 1. Okay. Now what does ML? What could ML equal? Yes. How many orbitals are in a p orbital? 3. Good. How many numbers do we have? 3. Now, how many electrons is that? 6 electrons. Perfect. So ms equals plus or minus 1/2, and I'm not going to draw it out for everyone, but essentially 2 times this number, you get 6 electrons.
Luke, I have a question again.
Yes.
Like you said, based off the orbitals, is that based off ML or just L? You're like, oh, how many orbitals does that one have? And it's like,
Oh yeah, it's based off of ml.
ML, okay.
This is the type of orbital. So this represents the p orbital.
Yeah.
L equal represents the p orbital. Ml represents the number of orbitals in that p orbital. After those things.
Wait, but then, so if you're adding like the 2 and the 6 like you did in the other one, it's 8, but this one only has 7.
Good. Very good. Okay. So then now, a good question would be, how do you represent the how should I say this? The electrons in the p orbital. How would you represent the 3p electrons in chlorine, right? So now what you would want to do is for this case, right? This ms one would be so
Do you just take out a like minus 1/2? Do you know what
no, yeah, no, I know what you're saying. You exactly do that, but you kind of have to. One way to write this out, this is going to be really annoying, is to just like kind of write out everything again, except now you put plus 1/2, minus 1/2, plus 1/2, minus 1. Really annoying because yes, you could do how would I do this, right? So basically, with the p orbital, right? The p orbital is represented with 3 orbitals, right? So how would you represent? So this is how you would represent this one, right? How would you represent one of these electrons, right? One of these electrons would be represented with this, right? So it would be ms equals plus 1/2 minus 1/2, right? So that would represent this orbital. How would you represent this orbital? Now, what you do is you do n equals 3, L equals 1, same stuff as before, but now you want to change the ML to what? 0, because that represents here. All right? Please get it. Okay. All right. MS right now would be what? Plus or minus 1/2. All right. So right, ML would represent this. What would this orbital represent? You guys know what this orbital represent? Like by the ML number? Like you know how ML can represent, right? ML can represent -1, 0, 1 in the p orbital, right? I said that this represents a 0. What would this one represent? -1. Yes. What would the other one represent? 1. Okay. Can you guys? It's kind of getting your brain a little bit. Okay, that's good. I know it's very like hard to understand at first because it's just like what the hell is going on with these numbers, but once you like practice a lot with this, you'll understand it. But now, yeah, let's represent this last one. This last one, there's only one spin to it, so it's very important. So can anyone tell me what this last one represent? L equals 1. Yeah, ML equals 1. So n equals 3, L would equal 1, ML equals 1. MS equals plus or minus 1. I mean,
Wait, but why is it plus?
no. I made a mistake there. Good catch. It's just 1/2. It could be either plus 1/2 or minus 1/2, but really doesn't matter. As long as you're representing one electron, represent that. All right? Is everyone following with this? Okay? Don't worry. All right? We're almost at the most complex example. I know this is no. They're not going to ask you like specifically this nonsense, right? They're going to ask you how would you represent the electrons in a 3p orbital? That's all they'll ask. I'm trying to teach you guys kind of like the thought process with this without going into tomorrow's lecture. Okay. Tomorrow's lecture is going to be 1s2, 2s2, 2p6. That's going to be wave mechanical stuff, which is stuff you guys. I wish you went over on the first lecture, but you know. No, you guys won't be lost from tomorrow. Tomorrow it's gonna make a little more sense, I hope. Okay. All right. I'm gonna stop screen sharing because I hope that the recording is not like. Okay. All right. So now let's do a 3D orbital. So let's do.
Wait, did we learn this?
Well, you guys did learn how to represent like what's it called, quantum numbers in D orbital, right? Like basically, now like let's say like we're doing the three like. How would you guys represent the 3D orbital?
And
N equals 3, right?
L is 2,
L equals 2.
ML is negative
Yes, ML is -2, -1. Okay, right? I'm just gonna draw this 1, 2, 3. There's 5 orbitals, right? So how many electrons? 10 electrons, perfect. Minus 1/2, plus or minus, plus or minus 1/2, plus or minus. Okay, you guys get the point, right?
Yeah, is that what they're gonna ask?
Yeah, they could ask like, how would you represent the electrons in the 3D orbital? All right. And then what they could do now is they can, tomorrow lecture, they're gonna ask you like, how do you represent the 3D electron in like vanadium, which is like this element here, V, right? How would you represent
2 dash.
yeah, but how would you represent that with quantum numbers? How would you represent the electrons with that? So no, not like the wave mechanical model, the quantum numbers. So like N equals. So let's just count the number of electrons. Yeah. How many electrons are in vanadium? 23. Okay, 23 electrons. All right. Okay. I'm kind of should. I don't know how to. Okay, let's go for it. So it's in the 4th principal energy level. So how many I guess how would you represent all of the electrons in vanadium? That's a good question. Yes.
Like 1s, 2s2, 2p6, 3s2, 6, 4s2, d3.
Yes, that's wave mechanical model. How would you represent that in terms of quantum numbers? How would you represent all the electrons? How many energy levels are there in vanadium? 4, right? There's 4 rows, right? Each row represents an energy level. All right. So a way to describe that is you could do 1, 2, 3, and 4. Okay. Are you guys following? This represents the number of energy levels. Okay. So
But L could be 0, 1, 2.
yeah, if you want to represent any of the electrons, if you want to represent a specific electron, you would have to pick one of those L numbers, right? So L could be 0, 1, 2, or 3. Okay? What 0 represents is s orbitals. 1 represents p orbitals. 2 represents d orbitals.
SPD.
My bad. I made a little mistake. Sorry. It's 1, 2, and 3.
Wait, why is there no?
There's no. Wait, no. There's. No, that's right. Okay. 0, 1. Oh yeah, there's an f orbital. I'm dumb. Okay. So 0 would represent the s orbital. 1 would represent the p orbital. 2 would represent the d orbital. 3 would represent the f orbital. Okay. Yes, s, p, d, f. Right. Okay. So now, with the ml, right? How many orbitals are in s orbital?
Oh,
Just the s1.
1. And just
0.
S.
Yeah, it would be just 0.
Oh, 0.
Yes. What about for the p orbital? It would be for just any p orbital.
Oh, negative.
-1
And 1.
and 1. Okay?
Because you have to do, if it's 1, you have to do the negative to the right.
Is everyone following with this? Okay? Are you guys okay? You guys alive? Okay. Okay. All right. Now let's try to represent. So this is P, this is S. What's the D one?
-2.
Yes, -2, negative. -2, -1, 0, 1, and 2. Okay? All right? And now the F1, you guys, you don't need to know this because in vanadium, there is no F orbital actually being used. A way to realize that is see, like, this is the F block. So anything that's not past this number, so like, let's say 57, right? If you go to 56, none of these electrons actually have an F orbital. Okay? But you guys don't need to worry about that right now. You can worry about that tomorrow. But yes, how would you represent the F orbital in this?
-3, -2.
Yes, -3, -2, -1, 0, -1.
No, one.
1.
Yes. It's a long day. I took an orgo test. My brain is fried. Okay, so how many orbitals are in the S1? 1. How many orbitals are in this one? 1 orbital. 3 orbital. How many in 5 orbitals? All right, and then 7 orbitals, right? It increases by 2, right? So how many electrons are in the S1?
2.
2. Okay. 2. How many is this? 6. How many is in this one? 10. How many is this? 14. Right? How did you guys get that? Because you multiplied by the MS number. Like there's plus and minus 1/2. Right? Yes, is everyone following this? Good, Devinder? Good on that? Yes, you don't need the F. The F doesn't represent any of them because there's no electrons in the F. Yes. Right. Thank you guys for coming. I appreciate you
Thank
guys.
you for your.
Please email me if you guys have questions. I'm more than happy to help out with that. Okay. I know that this is a very tough topic for you. Just whatever. Okay, next week is gonna be nice because next week you guys will learn actual chemistry. You guys will learn bonding. But that's beside the point. Okay, so anyways, for specifically vanadium, right? Vanadium, right? How many electrons are in the d orbital? Can anyone tell me that? Or does anyone know? Yeah. Yeah, 3. How did you get that?
No, one, two, that's 13.
Yeah, good, right? So what she just did there, right, is this is the D block, right? If you were to count this, there would be 10, right? And what I'm trying to convey to you all there is that it's not a coincidence that there's that many electrons and the periodic table is arranged with 10 right here, 2 right here, 6 right there, 14 right here. It's not a coincidence. It makes your life easier when you recognize that because you don't need to memorize anything. You can just know 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 4, 3d3, right? So these represent the 3d3 electrons, right? You guys,
3D3 you said.
yes. that's
Wait,
three.
yeah, that makes
Okay. So to represent at least one of these electrons, all right, how would you represent one of these 3d electrons in vanadium? Would anyone like to give it a shot?
like you want to go for it?
With quantum numbers, just in general. Like, tell me the base, like, start with n equals whatever.
N equals 3.
N equals 3, okay? L equals 2, ML would equal what?
-2 to positive 2.
Okay, but which, I'm asking for one specific electron. So what would you do? You could just do -2, or you could do 0.
Wait, why? Why just one thing?
Because if you're asking for a specific electron, right? How many each electron resides in one orbital, right? So why you're asking for only one is because if I'm asking for only if I'm asking for well actually we'll do 0 because 0 makes more sense with this case. But if I'm asking for a specific electron, right? You would have to do a specific orbital as well. What's that? It depends on the case. Obviously, we haven't gone over Hund's rule or Pauli exclusion principle or whatever nonsense that you guys will go over tomorrow. But it depends. Depends on the thing. I didn't. Okay. You're still new to the school. Okay, MS equals, what would MS equal? Good, exactly. That's,
Just one single electron.
yes, one singular electron. What this right here represents is it represents this electron, the third electron in the d orbital. All right, and to demonstrate that, I wish I could explain to you guys wave mechanical model, but you guys don't know it yet, so I'll.
Wait, so then how would you know if MS is plus one half or minus one half?
Doesn't matter.
Oh, it
Could
doesn't
be
matter.
either.
Okay.
But yeah. All right.
Wait, so like, what, is it the third electron? Because it's like the third spot on the D block.
Yes.
Okay, okay.
Third electron because it's the third spot on the D block. Okay. I highly recommend you guys familiarize yourself with using the periodic table to answer these quantum number questions. After tomorrow, you guys can make like a ton of questions for yourself about like doing quantum numbers, finding wave mechanical model, doing whatever.
Okay.
Yeah.
So when we're on like the top part of the periodic table, not including the lanthanoid series or actinoid series, that's only 1s, 2s, 2p, 3s, 3d. Like, are we only working within certain orbitals? Like, are we ever gonna touch like 4f? Say,
You guys could. You guys could totally touch 4S. It depends on the case that you're doing. So like if you're doing, for example,
we do 10.
10,
Yeah.
then you would not touch the 4F orbital. The reason it being, I could just tell just by looking at this, because you would have to pass one of these numbers. You would have to pass the lanthanoid or the acetone series to see that you're passing. Yeah. Yes. So Tim would not be one of those cases. They could ask you to do it. It'd be a really annoying question. I don't think he would ask, but don't take my word for it. Practice.
Okay.
But yes. Okay. Everyone chill. Everyone good. Good on time, kind of.
Oh, and then if you drew the like diagram for vanadium for the last orbital for 3D, it would just be 7. Would it be 7 boxes, and only 3 of them have electrons in it?
Last orbital in
Vanadium.
vanadium.
Yeah. So when you draw the boxes, it would be 5 boxes, right?
5 boxes. So with the boxes, vanadium, right? If you were to represent the 3D one, it would be 1, 2, 3, 4, right? So 5 boxes, right? How many electrons are in each orbital?
Well, for this one, only
Yes.
3.
Every orbital, every specific orbital has 2 electrons, right? So you guys don't know this rule yet, but that's Hund's rule. But basically, yeah, you need to fill up one of these at a time.
One at
So,
a time. Okay.
yeah.
No,
So it could be up or down. Oh, the reason why it can't be up or down, so it can be this way. But it can't be up or down because of a specific rule that you guys will learn. I think it's Pauli exclusion principle. Might be that. Yeah, it is Pauli exclusion
we
principle.
did do Pauli exclusion.
You guys did?
Yeah, that was part of the notes.
Oh.
And note 2, well, we learned just like the number format, not the actual diagram, but the concept that you can't have 2 of the same quantum numbers. Like no 2 electrons will have the same form on
Yeah,
it.
he didn't give us the diagram.
He didn't give us the diagram, he's like, that's just it.
Okay. Well, Pauli exclusion principle basically says that no electron, or no, that's not. I mean, yeah, no electron can have a positive and negative, like positive and positive, or negative and negative. The reason why it's going in like that is another rule that I'm forgetting. Either Hund's rule or some other rule. Hund's rule? Yeah, it's Hund's rule. Hund's rule states that like the electrons go in with the same spin and then they go in with the other spin. That's a very amateur way of explaining it. But yeah, yeah. Are you guys feeling okay with this?
Yeah, definitely better.
Definitely better. I know that this is a very like I don't even know how to describe it.
You go over degeneracy.
Hmm?
Degeneracy.
Degeneracy? Yeah. So do you guys understand the stuff I'm saying with the periodic table though? Like the how the periodic table is kind of a cheat sheet for all the stuff, for all the quantum numbers? Is everyone good with that? Okay,
Oh, the notes.
so,
That kind of.
No, I have it.
okay. So yeah, this is all the stuff.
Oh, and also, is he gonna ask us about like the electron mapping, like with the darker shaded?
Nah,
Okay.
you might ask like what it represents.
That one just threw me off.
So yes, with our new definitions, right? What would N represent? What does N represent, guys?
Principal energy.
Yes, energy level, right? On the periodic table, right? It shows the energy levels, right? What does L represent?
The orbital.
Oh, angular momentum.
The type of orbital, right? In this case, it says the shape of the orbital because S, right, has this kind of shape. P has like this kind of shape, right? D has like a bigger shape, right? They're saying specifies the shape. I'm saying specify the type of orbital, right? You have S orbitals, right? And then you have P orbitals and whatever orbital, right? What does ML represent?
Number of those types of work.
Number of those type of orbitals, or a more specific thing is those that would represent the orbital of the type of orbital. If that makes sense. So basically, like if you were to talk about the p orbital, right? How many? What would be the quantum numbers for 2p? Anyone tell me real quick?
N equals 2.
N equals 2, L equals what?
Or
1, right? What would ML be? Negative 1, 0, 1, right? It represents these boxes. Okay, that represents the orbital that the electron can reside in. Okay, so yeah, basically that. But I'm trying to tell you guys in a more practical manner what that actually means. All right. So now with the nodes, nodes are just nodes, nothing, nodes, right? Nodes represent a place where no electron can be found. Okay, very self-explanatory concept. It's just n equals n minus 1 and stuff like that. All right, quantum number, right? Quantum number. I mean not quantum number. The spin, right, represents whether the electron is up or down. And next lecture, you guys should hopefully do box orbitals because box orbitals are a very good way to convey where the electron is. But yeah. Yeah. Is a specific electron going up or down? That's essentially what the NS represents. Plus 1/2 can represent going up, but negative 1/2 can represent going down. Okay. And then yes, Pauli exclusion principles is no atom can have the same set of 4 quantum numbers. All right. So when I'm representing the 2p orbital, right? Each electron has its own specific set of quantum numbers. Basically, like your driver's license or something. You all have a unique driver's license or a unique. Actually, that's a terrible.
Unique ID number.
Yeah, you guys have a unique. You guys have a unique
Social security.
NYIT email, I think. So everyone has the same NYIT edu whatever nonsense. But then some people will have 01, 02, 03, and whatever, and then they'll have a specific name. Kind of similar with all these quantum numbers, and this Pauli exclusion principle means that nobody has the same email. I'm not gonna have the same email as Josiah or the same email as Spiro because that's just weird. All right. All right. So yeah, that's a summary of this. Okay. S orbitals are spherical. Okay. I don't know why. I mean, it's good to go over this
I
stuff.
kept saying, how do we know? How do we know? Because I don't know why I couldn't answer that.
What do you mean? How do we know?
Like he keeps putting in red. Like how do we know? Is it just by looking at the quantum numbers, or is there like another reason that I'm not?
How do we know the S looks like that?
No, like how do we know like the total number? I think
How do we know the total number of what?
like there's one S, and then there's like we call it 3 orbitals in P, 5 orbitals in D, 7 orbitals in F.
I don't know how to answer that question. That's beyond my scope. You don't need to know how. You just need to know Because with the periodic table that I showed you guys, that you guys will have in the test, you guys can see that will show you the framework of the S stuff, the SPDF, from what I showed you guys. All right. At least I hope that that was conveyed today, because yes, that's the most important thing. I don't really know why he keeps asking, how do we know? I mean, a good thing for this, right, is that, yeah, okay, I guess I guess it is. Wait. This is the first orbital of the people, and this is the second one, this is the third one. All right? It's the same thing as this, but represented in quantum whatever, right? 3 blocks. Okay. All right, moving on. Okay, why is there one p orbital? Because there just isn't. With quantum numbers, it doesn't show that. D orbital, right? D orbital, right? How many orbitals are in the D orbital? 5. 5, right? 1, 2, 3, 4, and 5. There are 5. That's what this is representing. There's 5 D orbitals in the thing. All right. Which one does it start showing up on? It starts showing up on the 3rd energy level. All right. No problem. See you, Josiah. Okay. So this is degeneracy. Essentially what degeneracy represents is that each orbital, each little like 1s2, the 1s orbital or the 2s orbital, there's different levels of energy in each orbital, right? If an electron's in the 1s orbital, it's closer to, I guess, if like, for example, how would I describe this? So basically with this, right, there's associated levels with each energy level, right? So 1s orbital would have a lower energy because it's close to just small, right? Next up is the 2s orbital, right? This has a larger energy, right? And then the 2p orbital you can have a greater energy because it's further away from the actual nucleus. Okay, so it has more energy. Think of like potential energy, right? If you were to drop the ball from here, it would be less energy than if you were to drop the ball. Potential energy, negative, right? Same thing with this, right? As you're increasing your orbitals, you're going further and further away from the nucleus, increasing the energy required to keep the electrons there, and also just increasing the energy of the overall electron. All right, so that's what degeneracy basically means. So does it only apply for yeah, it only applies with hydrogen. So in hydrogen, right, all the orbital energies in hydrogen atoms, these are equal to each other. But in the other electrons besides hydrogen, they're not so equal. So they could ask a question about what are the degenerate orbitals in the second energy level for hydrogen? You have to say 2s.
Oh, the scientists their equation.
No, there's no equation for that. You just have to know who did it and what the like findings.
So when you shine like a higher energy, like a higher energy light onto it. So there was a question on active, and I only knew the answer because of I searched it on other ones, but it was saying that you shoot it off with a higher energy or higher frequency light, that it has more kinetic energy going off.
So basically with the higher energy, right? So a higher frequency, what happens is there's more electrons. There's electrons being able to leave, right? And so what happens is basically like imagine, right? You see how like that bounced, right? It's the same thing. If I did it like here, not a lot of energy. But if I do it here, there'll be a lot more energy, right? Reason why is because this, right, gets converted to kinetic energy, it's whatever, right? Energy can convert things to kinetic energy, basically. So with that light beam, right? That light beam's going super fast, right? It's going in right that. So what happens is with the higher intensity, higher frequency, right? Frequency, the higher the frequency, the higher the energy, right? So because of that, that electron, that energy from the light is being converted to that electron to move it as kinetic energy away from it.
So then, in what case would more electrons come off as opposed to like higher kinetic energy?
You mean as opposed to higher?
Like the stronger light you shine on metal, does that mean more electrons are liberated? The higher.
Yeah. Yeah, you could totally just mean like that. Yeah, because you guys will learn hopefully tomorrow that ionization energy is a thing. And that basically means the energy required to remove an electron from an element. Yes.
All three of them are represented considered degenerate, or would it just matter in between, like 3s to 3p?
Sorry, can you repeat that one more time?
So if there's three orbitals, but they all three of them have the same energy, so would they be considered degenerate orbitals?
Yes.
Or even if it's only in 3p?
Oh, I see what you're saying. Generate orbital. Ah, I see. So what you're saying, right, is, are you talking about like these specific orbitals? So yes, yeah, they're all okay. So another way to describe this, right, is to say that. So I know what's really annoying is like the terminology, right? I keep saying type of orbital and then the specific orbital, right? All these three specific ones are also degenerate. So in this one, this is also all these three are degenerate orbitals. Okay, right? Same thing with here. This is also degenerate. These whole types of orbitals are degenerate, but in this it's not, right? The s orbital, there's nothing else degenerate with it. But the 3D orbital, there's 5 degenerate orbitals in there that all represent the same energy. All right. Okay. Yes, it's a tough thing. All right. All right. Are you guys good with this? Because that's it for now. Um. Okay. All these questions I'll put on the practice test or quiz. You guys didn't learn this. Okay. All right. I will end it here. I'm sorry, Zoom. We had technical difficulties once again. I will post the recording of this. I don't know how helpful the recording will be, but I hope that this is okay. I appreciate all of you guys that came. And yeah, I will.
You make sure that you know where.
I will post a recording of this so that you guys can see this. You guys can email me any questions you have, any comments about quantum numbers. I'm happy to help you guys. So yes, I hope you guys have a good
In the
day,
event that you don't
guys.
have it, it doesn't get lost, you can still access it from somewhere else.
Yeah, okay.
Do you guys have any questions, comments, concerns about anything? Anything about your test next week or about anything in general?
Do you know, are we like more stuff like that tomorrow in class or now?
No, so you guys are gonna move on. Now you guys are gonna move on to the 1s2, 2s2,
Sure.
2p6. And you guys are also gonna look at periodic table tracks.
Do you have any like, I guess I could also ask Professor Youssef, like other than doing like the active homeworks, do you have any like ways I could like practice more problems like that?
Yeah, so basically with the periodic table, you can literally just like be like, okay, let's try to identify what's it called? The valence electrons in copper. You know, and then what you could do is you can practice with whatever. You can see, what's like what's how many electrons do they have, you know, whatever, n equals 3, whatever. So you can do stuff like that. Yeah. Anything else?
So these are all generate.
Thanks. Bro, you good? Yes. Very quiet today. There's a lot. I appreciate you guys. Appreciate you guys. Was it helpful? Yeah? Okay. You can be honest with me and tell me it wasn't. And I can help you out. You learn stuff? Okay. Yeah. So chromium and copper. Yeah, it would apply. So basically, with those elements, you guys will learn this tomorrow. But chromium and copper are exceptions for like 1s, 2s2. Yeah. So basically, so you're familiar with like the wave mechanics model, right? So like, yeah. So mention would be 1s2, 2s2, 2p6, 3s2, 3p6, 4s1, and then 3d5. That's how you represent chromium. Copper is the same thing, except now it's 10, and then so it takes the electron from the 4s because it's more stable. You guys will put that high.
Okay, I remember that.
Yes. But same thing applies for like how would you represent this? Right? How would you represent this electron positive, right? So that you guys know how to do that. So okay. You guys are good. Okay, then you guys are chilling. All right? All right. See you, bro. Bye.
Have a good night.
Nice meeting you. Good night, guys.